Hello, and welcome to an old school presentation that centers around hacking an astronomical instrument to make it work on Mars. Specifically, to make it work for a Martian rover called Perseverance, and specifically hacking the printed circuit board technology to produce a fairly beautiful object, in my opinion. My Discord handle is Astrolabe. I'm an amateur astrolabist, and this is my website and my business email, where you can pick up one of these for yourself or for the astronomer in your life, because I'm fairly certain they probably don't have an instrument like this for Mars. All right, we're going to kick into the talk, and I'm going to give you an outline. That is, what is an astrolabe? Why would you make one? How are they made? What bits are what on them? How is an astrolabe used? What the equation of time is and how it relates, what unequal hours are, and what you have to do to rotate the celestial sphere to make it work for Mars. Then we'll close out with conclusions. That seems like a lot of slides, and it is, but fortunately, some of them are joke slides. So, we'll start out with what an astrolabe is. Traditionally, back in the day, we're talking a few millennia ago, they were brass instruments that were constructed out of plate, with lots of plates inside of them, and they contained information about the sun and the stars. Specifically, you could use them to locate the sun or some of the stars, major stars, indicated by the spiky bits on this one, for a given time and date, or vice versa. You could take a measurement of the sun or the stars and figure out what the time is. They were developed using techniques in the Middle East, including Greece. They spread around the Arabic world, or maybe they were built or innovated, inspired, and propagated by the Arabic world, including to North Africa, including through Europe, including all the way down to India. And they went to England, where they're recorded by the treatise for the astrolabe, written by this man Chaucer. This is a painting of him in the court of one of the kings. And he wrote a treatise for his 11-year-old son to introduce his son to astrolabes in English. And that kind of shows you that these instruments predate English as we know it as a language, the language that I am speaking to you in, and the language that I've learned in New Zealand and Australia to build astrolabes for those locations. They are endlessly surprising devices. I mentioned that they're made of plates. Those plates are held in place by pins, and those pins are shaped like horses, which I only learned after 3 years of studying these instruments, so pretty funny. Why would you build one? There's educational reasons, there's old school astronomical reasons. You can travel with them. They're a better sundial in that you can use them at night with the stars, and you can explain astronomical observations to somebody using one, and you can explore sort of mathematical concepts. But that's not the real reason. For me, it was YouTube. I was inspired by YouTube videos, specifically Uri Juchman's video, where he engraved his own, and by Click Springs Antikythera Mechanism episode, where I was started to think, in combination with these two, how would I put the moon on an astrolabe? Turns out it's a very difficult problem because the moon's orbit moves very fast in comparison to the Earth's orbit, and to accurately index that information mechanically is pretty difficult. At least on a gnomon, which is what this class of instruments is. The Antikythera mechanism did it again millennia ago and was dug up from underneath the ocean as the only surviving example of this class of instrument, except maybe for one geared astrolabe. But by this point in time, I concluded, bit of a difficult challenge for my current knowledge level. What if I tried to do it for a planet that was really tilted like Uranus. That could be interesting, but unfortunately, Uranus has no surface, so you can't visit it. Mars is visitable, has been visited by rovers, and is pretty niche, for example, for YouTube. Lastly, I might revisit this project and look at Venus because I've learned that Venus has also been locked over pretty heavily in its orbit, which does interesting things for building an astrolabe on a body like that. But it turns out that there are spots on Earth that satisfy that oddness criterion, which we'll see an example of later. Now, how are they made? Traditionally, they would have been involving a lot of hand calculation and tables that were calculated and distributed. This still happens, by the way, for like steam equations when you're teaching engineers. Steam tables. They were hand engraved with very intricate nets, which we highlighted earlier. Mathematically, you would take readings of and record celestial sphere data, and then you would, by stereographic projection, project them from a sphere onto a plane. Why would you do that? I believe it's because it's much easier to engrave a plane than it is to make an accurate circle, an accurate sphere with all the moving parts required. But spherical astrolabes do exist. There are examples of them. And the stereographic projection is illustrated in this cartoon here. It is an operation that moves by parametric equations points on the sphere to the plane. The plane. And these are the equations that describe it. Normally, you will only see the northern hemisphere, northern pole projection, northern hemisphere projection defined. But I went ahead and derived the southern hemisphere projection as well because that's where I live and that's what I was interested in. In modernity, though, we use laser cutters and computer programs and Chinese PCB fabs and transparent information plates to convey a lot of these information in a way that they couldn't back in the day. The last thing I wanted to point out in detail are these little holes that go up this center zenith, center azimuth, and I believe these are the center points for the scribe or the compass that was used to create these circles, each point for each circle, which is very cool and very interesting little artifact left on the device from its construction. One thing I wanted to point out is that they made a concentric display for calling out the overhead altitude lines, which is very interesting on this plate. Now, how do you use an astrolabe? I got this question after presenting to two audiences of 50 people both times, so I've rearranged the presentation to address this. Asterix, how do you use this version of an astrolabe? There are additional versions of astrolabes that you can read 12 ways, apparently, and there are universal astrolabes that are another class of astrolabe. This is not a universal astrolabe. This one is latitude specific, and in order to use it, you have to understand what parts represent what. We'll start with the spherical coordinates of the celestial sphere populated with stars. Those stars in this image are scaled and colored according to their brightness, their magnitude, and this celestial sphere is accurate throughout the whole solar system because space is pretty big. If you go out to the Voyager probes, which is like way out at the edge of the solar system, only Alpha and Beta Centauri have moved position slightly, which is crazy. Then, depending on which projection pole you choose, the stars will be mapped differently on whichever astrolabe hemisphere you prefer. Next important thing to add onto the spherical astrolabe is the tropics, and the tropics are defined by the furthest point that the sun reaches in terms of latitude on the celestial sphere. And I've kept the nomenclature of Tropic of Cancer and Tropic of Capricorn, but we'll see that it may be not so accurate in a bit. Now, depending on which pole you use, the Tropic of Cancer will be on the outside or the inside, and vice versa for the Capricorn. The normal edge of an astrolabe is the tropics, the outermost tropic, and I've extended it slightly further because I was using the moon's orbit, and that projects a bit further out. The next important point to put on an astrolabe is the ecliptic, which I've now added a second celestial sphere view here, so you can see it's circular and tilted. That is the plane that the sun and the planet of interest orbit around each other within. That projects two ways through the projection, depending on which pole you choose. And you can define interesting points like the solstices, the winter and summer solstices, and the equinoxes, because the equinoxes line up on the equator, which is also a one-to-one map. The equator is the projection of the planet's equator all the way out to the celestial sphere as well. I've added another shape called an analemma, which will be important later. It shows you how the apparent position of the sun relates to a regular equatorial time, which will make sense later, hopefully. It relates to the equation of time. That shape, when you project it, does not keep its shape, unlike circles, which is an interesting property. Another thing you can add are constellations. So these are drawn in 3D and then projected down to 2D. So their orientation and their size changes. Leo's larger here, Leo is smaller and flipped there. I've defined the zodiac, which is the band of constellations around the ecliptic by definition. And I spent time to put in an arc by the southern hemisphere for constellations that I'm familiar with that mostly line up with the Milky Way. When we've rotated the celestial sphere to work for Mars, we find that the northernmost constellation is not the Big Dipper or Ursa Major, as it is on Earth, but it is Cygnus, the goose, which is a good reference point to see if you have everything, well, if you've rotated the celestial sphere correctly for Mars. And with that rotation, we can see that maybe it would be more accurate to call one of the tropics the Tropic of Virgo, and the other one the Tropic of Pisces, if you were standing on Mars. Another piece that you need is the observer's projected horizon. So this is if you are standing at a certain latitude, in this case, Perseverance's latitude, which is about 18 degrees above the equator. And if you project your horizon standing at that point on the planet's surface, at that latitude on the planet's surface, then you can get your horizon projected out to the celestial sphere. You can have your zenith as well. And you can figure out what your lines of altitude and azimuth are. When you project that overhead hemisphere, you get a map for where celestial objects are for your local observation point. And there are two ways to do that projection, as there have been the whole way through. And I elected to have manufactured the sort of odd and more unconventional projection, which is still accurate. But more conventionally, you would have this more concave horizon. The last point I want to point out is that I projected the Roman numerals in the same way as the constellations, from 3D space down to 2D space, and I have them arrayed along the east to west azimuth. What's not normally depicted on an astrolabe is orbital information. I've added the orbital parameter information of Earth and Mercury to scale and projected them. They're not useful at all. They're just for scale and reference. and curiosity about the location of perihelion and nodes with the Earth ecliptic. These are very important traces to know if you are moving the celestial sphere from one planet to another. If you were actually trying to track the planet's location on an astrolabe, you would need the planets to lie along the ecliptic, and they would, depending on their orbits, travel with respect to the sun if they were inside your orbit or outside of your orbit. So where are all these parts put? Typically, you'll have the overhead hemisphere on the base with the handle. You'll have horizon markers, which will show you where a sun or a star will rise on your horizon. You'll have degree inclination around the outer edge. You'll have regular time for the equator, described in 24-hour time. And you'll also have something called unequal hours, which I'll dedicate a slide to later. You have a ruler, which helps you to make observations and make readings from the data. And then you'll have a sun and a star plate. I have the true anomaly dates for Mars on here every second day, because Mars has a year that's almost twice as long as Earth's. So how do you use an astrolabe, asterisk, to tell the time from a celestial reading? You can go vice versa with a bit of study. You have to take a celestial reading. So you can take a measurement of the sun, which is typically done through pinpricks or a tube lined along the ruler. And you will see the pinprick of light travel through the instrument. You'll take a reading, and you'll read off, in this example, that the sun is 45 degrees above the horizon in the morning. And you'll be able to tell that by where the sun is relative to your scenery. You will then need to know what date you are at. So you'll need to be keeping a separate clock synced to astronomical events like the equinoxes or the solstices. And I've picked the solstice here. If you are at the solstice, you will move the solstice point to 40 degrees above the horizon on your overhead map or picture for your observation. Then you will, this is a simplified version of that operation, line up your ruler with the intersection of the date and the altitude, and then you read off from the rim the time, the apparent time. Apparent as an apparition, where the sun is appearing in reality. And for that observation, it is roughly 8:25 a.m. Martian time, which is not the same as Earth time, because Mars rotates at a different speed to Earth. But that's not the full picture. If you want to get regular equatorial time, you have to apply the equation of time. And for the summer solstice, if we consult a chart showing the equation of time, we can see that we need to subtract about 15 to 20 minutes to get to regular Martian equatorial time, which is the analog of our time on Earth, which is a made-up system that is convenient. And then if you're at a high enough or low enough latitude and you're observing solar light savings, you would apply an hour forward or an hour backwards, however your local governance has determined, which would lead to maybe, 7:05 a.m. regular Martian equatorial time. But that's not important for the latitude that Perseverance is at. Now, what is this equation of time? Well, it's a direct readout of a phenomenon that occurs where if you take a photograph of the sun at the same irregular equatorial time each day throughout the course of a year, the pattern will be traced out in the sky. as the sun changes from low in the sky in winter to high in the sky in summer, and as it speeds up and slows down in its orbit. On Earth, that's this beautiful figure 8. On Mars, with different orbital parameters, is this teardrop shape. That shape has been observed on the mast of the Opportunity rover in this image here, which to me is insane. They took photographs every sol, the Martian equivalent of a day, and traced out that pattern. Crazy stuff. So how do you calculate or estimate the equation of time? Well, you have to account for two effects: the eccentricity effect, which is how a real planet moves and changes speed in its orbit compared to a fake sun that moves at a regular speed. And then you also have to compare how geometrically two suns moving at the same speed but at different tilts relate to each other to get towards the equator, the equatorial time. So I learned everything I know from Kevin Carney at his website, equationoftime.info. Highly recommend visiting it. It's an incredible resource. Did I get it right? No. I think I have a very simplistic estimation of it. And I know because I found Pierre Barbier's website where he implemented it, and you can see that the shapes are a bit more subtle. He's done that for every planet in the solar system, so that's a very useful resource. And he has this amazing and humbling quote that I will now repeat on his website. Abiding in the midst of ignorance, thinking themselves wise and learned, fools go aimlessly hither and thither, like blind led by the blind. Now, I consulted his references and found this book, which kept plaguing me, and it was Astronomical Algorithms. Foreshadowing, it's an important book. I wanted to devote some time to talk about what happens to the projection of the overhead hemisphere as you change your zenith, as you go away from the equator towards the poles. At the equator, you get this interesting projection where your horizon projects to a straight line. In Melbourne, you get something that's like quotation marks, a bit more conventional. And then at the poles, your entire overhead hemisphere is able to be displayed inside the Astrolabe. And at the poles, you get the situation where your overhead hemisphere does not always intersect with the sun on the ecliptic, which makes sense because you can have permanent nights and permanent days on at the poles. And this is what Uranus being tilted and Venus being tilted would look like if you built an astrolabe for it, except it can be more exaggerated. Now, I also wanted to talk about unequal hours because they're near and dear to my heart, and they come from this old concept where the length of hours in a day was not constant. In winter, it could be that the hours in a day were very short, while the hours in the night were very long, and vice versa. In the summer, the hours would be very long, and the night time hours would be very short. So seconds would change length throughout the year. And that was calculated by dividing the time between sunset and sunrise by 12. Physically, these things are latitude dependent. So at the equator, the length of the night is always the same length as the day, I believe. But in Melbourne, that changes throughout the course of the year. And mathematically, this length of the unequal hour is a function of the space that contains the sun and your horizon. So while these lines can be extended to meet your horizon, there would be very little point in diagramming that because the sun would never reach your horizon there. That is not always true. You can actually have the sun meet your horizon if you're at the poles. And when that happens, you get these beautiful curves, which show you that at the equinoxes, above and below them, a day or a night can be very, very short, and the rate at which they change speed is pretty substantial. Another interesting thing happens when the sun is either always above or below the horizon, and that is that the unequal hours become equal hours. You only have 12 hours in a day, and those hours are 2 hours long. Very interesting consequence of geometry and extending this function. The function breaks basically, but it still makes sense. So very interesting mathematical artifact there. Here's a blooper reel of all the fun I had trying to graphically illustrate these, graphically program these unequal hours, and the frustrations of pre-AI life, and probably still AI life, finding bugs in code. Now, I want to spend some time talking about the adaptations required to make an astrolabe work on Mars. The first thing to know is that the inclination of Mars, its tilt, its axial tilt from its orbital plane, is different compared to Earth. So that's the first change you need to make, and I did find a paper that did that. However, it's not the full picture. You both need to tilt and rotate the axis. First thing you need to do is find out where the North Pole of Mars is, which you can find out from the Astronomical Algorithms book. And then you need to find out where the orbit of Mars actually is in space, which you can do as pointed out earlier. But you need to move the North Pole of Mars to align with the North Pole of your projection while rotating all of the stars and the orbital information at the same time. And finally, you need to find the intersection of the Martian equator and its orbital plane and rotate that to be aligned with the vernal equinox of your celestial sphere. And that gets pretty tricky because where is the vernal equinox? It's not when the planet is passing from south to north in the east. It is when the planet is actually passing from north to south, looking towards the east. This is all very easy to say and hard to realize. I could be saying it wrong as well. Now, this brings me to my conclusions. Read textbooks. They make your life very easy, and they help you to work a lot more precisely. They stand on the shoulders of giants. Same for reading the literature. For astrolabists, the curriculum for building generalized astrolabes or exo-astrolabes, they're pretty fun, but the curriculum is not streamlined. And to build these, you can't use off-the-shelf tools, really. You've got to graphically program and be able to work with astronomical data, which is a fun little hobby. I'm going to close out with a saying from the indigenous people of New Zealand, or Aotearoa. Aim for the stars, lest you miss, you will hit a lofty mountain. Which is to say, aim high, be ambitious, and follow your interests. Thank you very much for your time. QR code to my website if you're curious in investigating these a bit more. And thank you for your time. I hope I've done a bit of edutainment and interested you more in our solar system.